Hey, Tyson. We miss you.
No, we don't.
You have one, right?
Girl, you are on this.
All right, while Marina looks for her notes, I'm just going to quick recap this theorem. So, yep.
Yes! It's a miracle. I do.
I do, and I just forget where I
I have that notebook with me. It's in my locker.
This theorem holds the hypothesis that as long as f is continuous, then we can conclude the intermediate value theorem. Okay? So the first thing we always have to do if we want to use this theorem, we have to state that the function is continuous on whatever interval they specify. Then what we do is we take that interval and we find the outputs, so like f of a and f of b, and then we can conclude that there's going to be some value, it's just k is what they use in the theorem, some value k that's in between those, that output could be logged back, I guess, to an input that's going to be in that interval. That's what this theorem says. So we mentioned a lot of times it's used to locate zeros. If you have like an output, let me just draw a quick picture. Let's say f of a is down here, and then f of b is up here. So this is what it's used a lot for. Is, all right, f of a is a negative value, so that's what it's saying, it's like differs in sign. F of b is a positive value, so obviously 0 lies between that. So we can always back trace it to some value in that interval that's going to give us that output, is basically what it's used for. Okay, so we're going to do like 2 examples together of this theorem. And I think I mentioned yesterday, I've seen this shown up on FRQs, having to use this theorem, and you have to like go through the steps of like stating a hypothesis is met. So this one says, use the IDT, intermediate value theorem, to show that the polynomial function, this cubic, has a 0 somewhere on the interval from 0 to 1. All right, so before we can even use this theorem, I have to show that the function's continuous. So I'm going to like number this as 1. Referencing back to this page, this is what we have to do first. You have to state the function, so I'm just going to use f of x, that was the notation they used, is continuous on the interval 0 to 1 because, any ideas why that's continuous there? Good job! Because it's a polynomial function, and polynomial functions are continuous everywhere. All you have to say is it's a polynomial. If you wanted to, you wouldn't have to for the AP exam, but maybe just for your own notes. Polynomials are continuous everywhere. So that's what we have to say. Hypothesis is met. Then we get to use the conclusion. So we have to basically find next f of a and f of b, where a and b are the values that they give me on the interval. So this would be a, this would be b. So second, I usually just start by finding f of a. So f of 0, I'd use my equation, is 0 cubed plus 2 times 0 minus 1. F of 0 is negative 1. Okay, so there's my output at my left end part of my interval. Then I gotta find f of b, so we're just gonna come over here. So f of 1, plug it into your equation. You get out 2. Okay, so what we're trying to show is that it has a 0, which is like an x-intercept or an output of 0 in that interval. So do you guys agree that 0 lies between these two outputs? Yep. Okay, 0 lies between these two outputs. So another way you could write this and what you should show is that 0 lies between f of 0, which was -1, and f of 1. So first you got to state that. Second, you have to show that. Then you can use the conclusion. So since this is true, therefore, the intermediate value theorem guarantees there is at least one x equals c. And this is literally the wordage I use every time I use this theorem. Therefore, IVT guarantees there is at least one x equals 0 such that, and then I kind of fill in how it's applied to this specific problem, such that f of c would give me 0. Okay, let's pretend. Well, actually, it doesn't. Well, on the next one it does. Sometimes I might ask you to find the value of c. Sometimes I ask you to find the value of c, and then you could use your graphing calculator like for this one, but we'll do it on the next one. All right, so hypothesis has to be continued. Second, you have to show that whatever they're asking you lies in the interval, and then you can guarantee there's some value c that's in between a and b that gives me an output of 0. Okay, can that make sense? Let's try another one. Verify that the IVT, intermediate value theorem, applies to the indicated interval, and then find the value of c guaranteed by the theorem. So here's my function. Here's my interval. And they're saying, show us there's some value c that has an output of 11. Okay, let's see if this holds. First, I gotta state it's continuous on the interval. Why is this one continuous? It's a polynomial, yep. We'll look at some examples later on with more theorems of when it's not a polynomial, so if you're worried about that, don't worry. Polynomials are continuous everywhere. All right, second, what we have to do after that, you have to find the outputs of your endpoints on your interval. So you got to find f of 0, which is considered your A, and f of 5, which is considered your B. So that's where you're always going to go next. All right, I'm just going to start with 0. There's my equation. F of 0 is -1. 5 is 29. So does the output 11 lie between those? Yes. So the output of 11 lies between f of 0 and f of 5. So then we can use the intermediate value theorem. So again, I'm going to kind of use like my cookie cutter response here. Therefore, the intermediate value theorem guarantees there is, yeah. Yeah, you do have to do that. I'm gonna just like memorize that first part. Such that f of c equals 11. Okay, we're not done with the problem though. Now we have to find the value of c. Well, f of c would mean just plug c in here. So like this, folks, would just be c squared plus c minus 1, and we know that equals 11. Okay, so we can actually do by hand. If you want to use the variable x, you can. It doesn't matter. This one we can factor. So minus 11 more. Okay, so I get two c values. 3, -4, yep. Which one is in my interval 0 to 5? Yep, 3. So. So that'd be my answer. So guys, if you can't solve it by hand, you can just do it on your graphing calculator. You want to do this one where you have to use your graphing calculator to solve it? Sorry. This one. Okay, might as well. So this one, if you were asked to find the C, f of c would be c cubed plus 2c minus 1. And in this case, we're trying to figure out if that was equal to 0. So this, you don't know how to factor. So this, you would just type into your y1 and figure out when it equals 0. And obviously, like, on the AP exam, if it's something you can't solve by hand, it would be a graphing calculator problem. And you're only, if there's more than one, I don't know if there is, I can probably tell by looking at it. Is there more than one? No, there's just one. Obviously, we're only looking for the one that's on the interval 0 to 1. All right, so is x cubed, is it plus 2x minus 1? Okay. All right, so we want to figure out when that equals 0. So we calculate the 0. You just have to go to the left of the 0 or like kind of below the 0, above. So it would be C is approximately, let's practice our rounding rules, 0.45. You just copy the first 4 digits, dot, dot, dot. So that's how you do it if you're asked to solve it by hand. All right, that's a theorem. There's like maybe 2, 3 of them. Whoop-da! What an important section. 25 slides of greatness. 70? I don't think it's 7. I don't think it's that much. I know the 1.5 one's pretty short. So I just posted that. So they copy and paste it. I was like, that looks short. You'll be okay. All right, I'm going to let you guys do this warm-up quick. Oh, 2 warm-up problems. Good stuff. Maybe like a good 5 minutes to try this. First one looks sticky. doing? On the first one, my hint is you should be looking at the left and the right hand limits. So if you started with that, that's good. Should be looking at, since this is a piecewise, this looks like possible jump discontinuity. So if I want to find a limit, I just have to make sure the left and the right hand are approaching the same thing. So you should just make sure that that's the same as x pushes 3 from the right. Okay. For the first one, 3 from the left, that would be everything less than 3, so I'd use this top piece. 3 from the right would be everything to the right, or greater than 3. So what am I saying? So I'd use this piece. Okay, both of these you could just direct substitute 3 in. This side you should have gotten 9. This side, all right, you guys. What's the cosine of pi? Cosine is x, -1. So they did equal the same thing. So this whole limit was 9. Eight minus -1 would be 9. Okay, good with that one? The next one, these are the ones I like. These ones are kind of fun. Find the value of a that makes a function continuous everywhere. So I see the top part, polynomial, so it's continuous everywhere. Bottom part, another polynomial, continuous everywhere. But this piecewise function, what we gotta look out for is jump discontinuity. The only point it could be discontinuous is at 2. All right, so what we have to do is we have to figure out the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. And we're basically going to algebraically figure out what a needs to be so that these are the same. So basically just make the ends meet. Okay, so 2 from the left, I'd use that top piece. 2 from the right, I'd use the bottom piece. When you do the direct substitute, remember you're only plugging it in for x. All right, so here I get 6 plus a. Here I get, let's see, 8a minus 4. Solving that, I got a to be 10/7. 10/7. And then you can like check your answer if you want by finding f of a. And then just be careful here though. You'd have to plug back in a like here to make sure the limits are the same thing as the actual output. Okay. So 10/7. Do we get that one? I like those ones. All right. So we're gonna start this lesson because I feel like between today and then our shortened class period tomorrow, we can probably finish it. It's definitely shorter than the last one. And I already introduced you to this. Infinite limits. So we're basically gonna like study deeper those limits that like go off to positive or negative infinity. And then we're gonna talk about like how that relates and how that can find like asymptotes. Okay, we've already talked about like this type of discontinuity. So this whole section is designated just to diving deeper into what we call like those infinite limits and then how they can help us find vertical asymptotes. Okay, so again, just kind of like a little review of what this like looks like on a graph. You know, it could look something like this. As we're getting close, let's see, this one's 2. My function's going off to either positive infinity or negative infinity. On a table, they either get like really, really, really big, increase without bound, or they get really, really, really big. I always call like negative 3,000 big in the negative direction, is how I like to think of it. Instead of like thinking of negative 3,000 as like a very small number, it's a very big number in the negative direction. That's like a calculus way of thinking it. So that's kind of what it looks like on a table. So we know that a limit can equal infinity as long as they're going off in the same directions from the left or to the right. But again, here's like the differ in some textbooks. Some textbooks say the limits have to equal a number, a numerical value, and some people don't consider infinite a number because it never goes on forever. So remember, this also could be does not exist, classified as both. The AP exam uses both. Our textbook says it can be infinity, and that's kind of how I'm used to looking at it. But it could also be classified as does not exist. All right, that's just kind of a little review. It's what we call infinite limits. So let's try this one. Now that we kind of know left and right hand limits a little bit better. Yes. Oh no, does it say page 2 at the bottom? Oh no! Do you have all the other ones? Does it say 4 or 5? Yeah. Oh shoot. Okay, I'm gonna pause this video and go print these out quick. Sorry. That happened on, this is so sad. Oh, I don't know how to pause. Am I boring you?
And the only other classic form of sleeping is just
Oh. Going to act more excited. The only thing I wrote on here is like these could also be like does not exist. Oh sorry. Pass around. One other thing I did write down that you can write down. Now applying this to like left hand and right hand limits. This would be like the limit as x approaches 2 from the left of my function is going off towards negative infinity.
R.
Did it run out of staples? Okay. So you can now see this, now that we kind of know what left and right hand limits are too. You could see the limit as x approaches 2 from the left, maybe that's going off to negative infinity, but the one from the right is going off to positive infinity. And really the idea behind this, guys, what we're like leading towards now that we kind of understand limits, we've looked at a couple, is now we're going to apply this to like help us find vertical asymptotes. You learned the pre-calculus way of finding vertical asymptotes, and now basically you're going to learn how we can use limits to find them. And limits allow us to find vertical asymptotes for like all types of functions.
Did you resume the recording?
I can't remember now. I think I did. Yeah, I did. It's recording. Okay. So let's just try a couple of these. So it says determine the limit of each function shown in the figure as x approaches 1 from the left and from the right. And now we kind of, like I said, understand this notation better. So I'm going to start with graph A over here. So the limit as x approaches 1, let's go from the left first. You can either write in f of x or we can actually write in what the equation is. I just did f of x. Okay, what do we think, guys? 1 from the left. What's this approaching? Yeah, you're right. Positive infinity. All right, what about as x approaches 1 from the right? Also positive infinity. It doesn't ask us to do this, but overall, the limit as x approaches 1 then would be positive infinity or technically does not exist. All right, B. 1 from the left of this one. What do we think? Positive infinity from the left. What about 1 from the right? Negative infinity. So that overall limit for sure would not exist. Okay, that's just kind of a little review over these. We talked about that before. All right, so here's where our vertical asymptotes come into play. This is a calculus way of locating vertical asymptotes. We can figure out that a vertical x equals a, so equation vertical asymptote, is a graph of the function if we check the left and right hand limits of that a value and see if they're going off to infinity. Okay, this is the calculus way of finding asymptotes. Couple little reminders about vertical asymptotes. Functions cannot cross or touch vertical asymptotes. Remember how we looked at horizontal and slant asymptotes? Those are a little different, but vertical asymptotes, a function cannot touch those. All right, so here's just a little walk you through it. Consider these two functions here. The behavior of the function is the same on either side of x equals 2. They're both going off to positive infinity. So we say, oh no, I just erased that star. There you go. So we say that the limit as x approaches 2 is infinity, or we could classify this as does not exist. All right. If I have something like on the right-hand side, the behavior of the function is different from each side. So we would say this limit does not exist because the left and the right hand are not the same. All right, so after you write that down, I want you to write down this underneath here, and this is a very important thing. I'm going to write it in red. It's so important. And I'll kind of explain what it means. Do the absolute value of a divided by a negative tiny number and then do like an equals arrow negative infinity. Okay. I'll kind of explain what it means after you write it down. If you have an a divided by a positive tiny number, that's going to go off towards infinity. And then if you have some value divided by positive or negative, a very large value, that's going to go off towards 0. Okay, so up top, those all say the absolute value of a, and then divided by. And this is basically like the algebraic or numerical, I don't want to say numerical acceptance table. This is going to be the algebraic way of how you're going to find these asymptotes. How you're going to find these infinite limits when you're not given a picture. So this is going to be like your best friend cheat sheet for like the next week when you're doing these. And obviously you'll start to memorize them after you do so many of them. But, so basically what this is saying is like, if you have any sort of value up top, like any sort of number, let's just say we have 4. I'll show this to you. And I take 4 and I divide it by a negative tiny number. So let's go like negative 0.000001, something like that. So I have any number divided by a negative tiny number, that's going to go very big in the negative direction. Okay. You know, let's say I have 7 divided by a very negative tiny number. Again, very big. Scientific notation so big. Very big in the negative direction. That's what this is saying. Because you're going to do these algebraically in a second here. So if you have a number divided by a negative tiny number, it's going to go off towards negative infinity. Similarly, if you have a number divided by a positive tiny number, that's going to be very big in the positive direction. It's going to be a very large number. It's going to go off towards infinity. Okay. Now, if I have any number, and if I divide it by a very large number, that's going to give me a really, 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 really tiny number, and that's going to get super, super close to 0. Okay? And if you ever get these mixed up, I can't remember which of my students last year was like, I just never remember them. So they just use their calculator and like did an example quick. They're like, oh yeah. 95 divided by a really big number, that's very close to 0. Okay? All right, here's an example of doing this algebraically. So it says, find the vertical asymptotes, if any, of the graph of the function. So you know how to do this the pre-calculus way, okay? You would normally factor your numerator, factor your denominator. The top doesn't factor. It's prime, sum of squares, but the bottom does. And then anything that's left on the bottom of these are vertical asymptotes. Okay? So the calculus way of doing this is by using limits. So you have to start by finding, like, when do you have your denominator equal to 0? Pretty similar to, like, what you did in pre-calc. When is this equal to 0? And we know that's at positive negative 1. So here's the calculus way of doing it. And obviously this is how you're going to have to do it moving forward. Let's start with positive 1. You're going to have to find the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. And if we can show that these go off to infinity or negative infinity, then we can conclude there's an asymptote. Okay, because then we're essentially proving this behavior of our graph. Oh, they're going off towards infinity or negative infinity, therefore there's going to be an asymptote there. Okay, so let's start with 1 from the right. And you can write out this equation if you want. I'm just going to use h of x. So, obviously, I can't plug in 1 directly, right? If I plug in 1 directly, I get 0 in my denominator. And there's no algebra I can do here. The top doesn't factor, nothing cancels out. So what we do in this case is we just pick a number pretty close to 1 from the left-hand side. So I always stick with like 4 decimal places. So coming on to 1 from the left would be a number just smaller than 1. So do 0.9999. So this is what I do if there's not any algebra I can do to try and direct substitute this. So you can either plug it into like this version of your equation or the factored version. It doesn't matter. I did it just in the original version. So if I have 0.9999 squared, minus 1, and then I have 0.9999 squared plus 1. All right, so this is obvious. A 0.99999 squared is going to be really close to 1, but just a little less than 1, right? Just a little less than 1. And if you need to type it in your calculator to prove that to yourself, you can. This is going to be a little bit less than 1. So up top, that's going to get close to 2. So it's pretty close to 1, a little less. What about on bottom? If I have something that's like pretty close to 1, but just a little under, minus 1, that's going to give me a negative tiny number. With me? And again, if you need to type these in your calculator to start, to get your brain to like wrap around this like concept, you can. It's going to give me a negative tiny number. So if I have 2 divided by a negative tiny, 2 divided by a negative tiny, that's going to go off. That's going to give me a really big number in the negative direction. So that's going to go off to negative 50, that limit. Okay, that's how you do these. Move this over a little bit. Okay. So then we're going to do the same thing for the right-hand side of that limit. So I'm going to use a number just a little bit bigger than 1. So again, I always do 4 decimal places because that's the rounding rule anyways. I just try to keep it consistent, keep it easy for myself. All right. So this time when I square 1.0001, I'm going to get a number that's just a little bit more than 1. A little bit more than 1. Okay, so up top I'm still going to get something close to 2, because this is going to be a little bit more than 1, plus 1, 2. A little bit more than 1, minus 1, I'm going to get a positive tiny number. So positive 2 divided by a positive tiny would go off to positive infinity. Okay, so what we just found, you don't have to write this down, but at 1, coming in from the left-hand side, it went down towards negative infinity, right-hand side, so therefore, there's going to be an asymptote there. Okay, that's what we're finding. All right, we'll stop there. We only have 1 minute. If these aren't infinities, then there's not an asymptote. We'll look at an example like that. We're not done with this one. We'll have to check -1 too, but we're at a good stopping point here.